Good day, everyone. Welcome to lecture number 32 of Theory of Computation. And in this particular lecture, we will be discussing about the recursively enumerable language and a recursive language. We will also discuss universal Turing machines. Okay. So let me recap what we have done about the recursively enumerable and recursive language. So we have recursively enumerable language, which are written as RE. So what is a recursively enumerable language? So it is a language, or we can say set of language for which a Turing machine exists. Or we can say that if we have a language, okay, language means set of strings. And if we have a Turing machine such that if we give a string as input to this Turing machine, so if that string belongs to the language, then Turing machine accepts the language. Accepts means that it will go into the accept state. Go into the accept state. Okay. However, if a string does not belong to the language, then that means Turing machine rejects the string, or we can say Turing machine does not accept. What is the meaning of does not accept? Does not accept means it either rejects the string or it loops on that string. Okay. So the set of languages for which there exists a Turing machine are called recursively enumerable languages. Then there is a subset of these languages which are called recursive languages, or we can say R language. So what are R languages? Any language is called an R language. A language is a recursive language, such that there exists a Turing machine for that language, and that Turing machine halts on all possible inputs. What does that mean? It means that if we have a language, let's say we have a language L1. So if this language is R language, then what does that mean? It means that there exists a Turing machine. So this is a Turing machine. Okay. Let's say the Turing machine is M1. And if I give an input to this machine, okay, it either accepts the input, accepts means goes into an accept state, or it rejects the string. Rejects means it goes into the reject state. So that means if there is a string W that belongs to this language, which is a recursive language. So that means if I give this W to a Turing machine, then the Turing machine goes into accept state. Okay. Accept state and halts. Accept state means it halts. And if I give a string, any other input which does not belong to the language, to the Turing machine, to this particular Turing machine, then this Turing machine rejects the string. Rejects the string means it goes into a reject state. Reject state means it halts. So that means this Turing machine halts for all possible inputs. So there is no loop. Okay. So what does that mean? It means that for recursive language, these kind of languages, so these languages which are also called decidable languages, and these languages, recursively enumerable languages, these are also called recognizable languages. Recognizable means that there is some Turing machine that recognizes the language. So these are called a recognizable languages, and our languages are called a decidable languages. And the Turing machine for a R language is also called a decider. Okay. So that means for this kind of language, R kind of language, so if we have an R kind of language, so for R language, we have an algorithm to decide the membership problem, or we can say to decide the membership. What does that mean? It means that for our type of language, if I give any string, I can decide. So if I have a language L1, so let's say this is a recursive language. Okay. Now, if I am given some string, I have to say whether this string belongs to L1. So this is a membership problem. Whether this string belongs to L1. What I will do, I will take a Turing machine of this language, of L1 language, and I will give this W to this Turing machine. Okay. And if Turing machine accepts, we will say it belongs to the language. Or if Turing machine rejects, we will say W does not belong to L1. So accept the case, we will say W belongs to L1. So that means we can easily have an algorithm to find the membership of a string in a language if that language is a recursive language. However, if a language is recursively enumerable, but not recursive, so it is recursively enumerable. What does that mean? We have a language L1. So I am saying it is recursively enumerable. Recursively enumerable means that whatever string belongs to the language, Turing machine accepts that string. And whatever string does not belong to this language, Turing machine does not accept that string. Does not accept means it either rejects or loops. Okay. So now let's see if we can decide a membership for a recursively enumerable language. Can we decide? So we have a recursively enumerable language. So we have L1, a recursively enumerable language, but not recursive. But not recursive. Okay. So it means that if I take input W, now I have to say whether this string belongs to L1. So same membership problem. Can I have an algorithm to say whether W belongs to L1? Now let's say we have an algorithm. Let's say we have a Turing machine that recognizes this string, this language L1. Because it is recursively enumerable, that means there exists a Turing machine that recognizes this particular language. Now let's take this string W. Okay, I will give this W to Turing machine. Now if W belongs to L1, this Turing machine will go into accept state. So that means if W belongs to L1, we can easily answer yes if W belongs to L. So that means if W is a string in this language, then we will give this W to this Turing machine. And if it goes into an accept state, we will say that this W belongs to L1. Now, if Turing machine does not go into an accept state, because there is a possibility it will go into a reject or loop. So in this particular case, can we say whether W belongs to L1? So if it goes into a reject state, we will say W does not belong to L1. Okay, if it goes into a reject state. However, if it goes into a loop, loop means we don't know whether it accepts it or rejects it. So that means there is a problem here. Problem here. So here we cannot decide whether W belongs to L1 or W does not belong to L1. When is this scenario? When W takes the Turing machine into a loop. So then we cannot decide whether W belongs to the language or W does not belong to the language. So that means for these kind of languages, recursively enumerable languages, it is easy to answer yes. So easy to answer yes. However, a problem arises if that string goes into a loop. So that means for such kind of problems, deciding membership is undecidable. Undecidable means we cannot solve this problem. We cannot say which string belongs to the language and which string does not belong to the language. Okay. So we have an important point here that for recursively enumerable language, for recursive language, it is easy to solve membership problem. But for recursively enumerable languages, membership problem is undecidable. Undecidable means we cannot solve it. There does not exist any algorithm. Okay, so membership problem is undecidable. But we have an important observation that for such kind of strings, for such kind of language, answering yes answers can be easily verified. Yes answers can be easily verified. So what does that mean? Yes answers can be easily verified. It means that if I have a string W, I have to say whether this string belongs to L1. So yes means when this string belongs to L1. No means that when this string does not belong to L1. Yes can be said easily. So we can easily verify whether this string belongs to the language. Okay. But solving a complete membership problem is a difficult task. Okay. So we have another observation from here that for some problems, okay, verification is easy, or yes answer verification is easy, but that problem itself can be an undecidable problem. We will be discussing this in great detail in our we can say the complexity theory, where we will be discussing about the NP problems, P problems. There you will say how verification is easy and how actually solving a problem is difficult. Okay. So this was about the recursively enumerable and recursive languages. Fine. Now we have one thing that we have to discuss. Basically, we have to say, so if these are our languages, so let's say these are the all possible languages in the world. All possible languages. Okay. Now I have said that this is all possible languages, or we can say all possible problems. So from these languages, we have languages that can be recognized by some Turing machine. Okay, so we have another set here, and this set means the language such that these languages are recognized by some Turing machine, or we can say by some computational device. In other words, we can say that these are the problems that are solved by some computational device, and these problems are called recursively enumerable problems. Now, recursively enumerable problems, there is a subset of these also, which are the problems such that, so these are the problems such that there exists a Turing machine, and that Turing machine halts for all possible inputs. So these languages are called recursive languages. Then we have a subset of recursive languages. Okay, and this subset is non-deterministic context-free language. So for non-deterministic context-free language, we have non-deterministic push-down automaton. Then we have another subset, that is subset of this, and this is the language that are recognized by deterministic push-down automata. These are also called a deterministic context-free languages. And the subset of this is, the final subset is this, which are regular language. So let me write it here. We know that regular language, so we already know that a regular language is a subset of deterministic context-free language. Why it is a subset of deterministic context-free language? Because we know, and it is a proper subset. Proper subset means that these are not equal. Okay, so why these are not equal? The first thing is that there is one context-free language that is not recursive language. Not only one, there are many, but I can give one example. For example, WCWR. This is deterministic context-free language, but not regular. Now we have deterministic context-free language. It is a subset of non-deterministic context-free language and proper subset. Why? Because all deterministic context-free languages are also accepted by non-deterministic push-down automata. So that means every deterministic language is also a non-deterministic context-free language. But reverse is not true. Why? Because there is one language, at least one language, and the example is this. This is non-deterministic context-free language, but not deterministic context-free language. Okay. Now we have another thing that non-deterministic context-free language is a subset of proper subset of regular language. Okay, so it is easy to verify, but reverse is not true. So it is a proper subset. Proper subset means that all non-deterministic context-free languages are recursive language, but reverse is not true. Reverse is not true because there is one language, and which is that language? This particular language: A raised power n, B raised power n, C raised power n. This is an R language, but not non-deterministic context-free language. Okay. Now comes R is a subset of recursively enumerable language. So what I am saying that all R languages are recursively enumerable as well, but reverse is not true. Reverse is not true. Okay, but we have not proven it yet. This reverse is not true. Reverse is not true means that we need one language. So we want a language that is recursively enumerable, but not recursive. Okay. Now we have to find it out. We will do it. Please wait a second. Now the last thing is that recursively enumerable languages are subset of all possible languages. So what does that mean? All recursively enumerable languages are languages, but reverse is not true. What does that mean? Reverse is not true. It means that there exists a language. So there is a language which is not recursively enumerable. So we are saying there. So let me write it in red. There exists a language that is not recursive. That is not recursively enumerable. So let's say this language is L1 and this language is L2. In this figure, in this diagram, that means L2 exists here. So L2 is a language, but it is not a recursively enumerable. And L1 is a language that is recursively enumerable, but not recursive. So we have to find L1 and okay. That will be the main focus of this particular lecture. So our main aim is to find L1 and L2. So whatever we are going to discuss next, that means we are discussing it so that we can find out these two languages. A language that is recursively enumerable but not recursive, and a language that is not recursively enumerable. Okay. So to answer these questions, let's start a new discussion. So basically, we will start discussion about the model for solving decision problems. So I am writing it here, model for solving decision problems. So we can break down every problem into a decision problem. Okay. So basically, we will first understand how to make a model for solving decision problems. But before that, you have to understand what is a decision problem. We know that decision problem is a problem for which the answer is yes or no. And to understand the model for decision problems, we have to first know that we have a Turing machine. Okay, let's say we have a Turing machine that halts on every input. Halts on every input. because we know that to solve a decision problem, it should halt on every input. Then only we can solve every problem. If it goes into a loop, we won't be able to answer the question. Okay, so we have a Turing machine. Turing machine takes an input, okay, and it either accepts the input or rejects the input. These are the two outputs from the Turing machine. Now we want a model for decision problems. So that means we want a decision problem, or we want a model. Let's say this is our model, computational model. And this computational model takes input the problem, or we can say the problem statement, and the output is yes or no. So this is the decision problem. Okay, fine. So it takes the input is a problem, and it says yes or no. So let's replace this computational model by a Turing machine. So this is our Turing machine. Turing machine that halts on every input. And the accept, so it was giving two outputs, accept and reject. Let's say accept is as yes and reject as no. And the input is this problem. So we have an input. So if Turing machine accepts the input, it gives yes answer. If yes means accept. So if it rejects an input, it gives no answer. But our Turing machine takes an input. So here input is a problem. So problem can be a statement. For example, if I have 3 employees and I have 4 tasks, so I can ask a problem, can we complete 4 tasks? So it is a decision problem. Decision problem, it has yes or no answer. So it is a statement. So we want that this statement should be given as input to a Turing machine, and Turing machine will give us the answer yes or no, accept or reject. But the problem is that how to represent this input, how to represent input. Okay, how can we represent this input? Because we should first know the type of input, then only we can design a Turing machine for that input that can answer yes or no. Okay, so to answer this, to understand this, how to represent an input, we have to understand how computers take the instructions, or how computers process the data. Okay, now we know that for computers everything is binary. So for all our computers everything is binary. Binary means 0 and 1. So if we have any object, instead of processing this object, computer converts this object into binary. So let's say object is our number. For example, object is 4. It converts 4 into binary. Okay. Now this 4, its binary is 100. So this is also called encoding of the object. So it is binary representation, encoding of the object. So if I have an object, so let me rewrite it here. I have an object 1. And its encoding is 10001. Let's see. So we write it like this. This one. We write it like this. So it means, this means in these brackets, it means encoding of object 1. Okay. Now let's suppose our computer has to process 2 or 3 objects together. So it has object 1, object 2, object 3. Okay. So instead of processing these objects, it will convert these into encodings. So like this. So this is the encoding of these 3 objects together. And this encoding, this binary goes as input to a computer, and then our computer processes this binary. So that means these statements, so it is a statement, this statement can also be converted into binary, or we can say it is encoding. And this encoding can be given as input to a Turing machine, and then Turing machine can accept this input or reject this input. So we can say, instead of saying the statements, we can say that every Turing machine processes binary input. Binary input. Why? Because every object in the world can be converted into binary, and that object can be given as input to a Turing machine, and then our Turing machine can decide whatever it has to decide based on the input. Not only this, even our Turing machine. So what I am saying here, that everything or every object has an encoding, or every component has an encoding, every data has an encoding. Okay. Since our Turing machine is also an object, or we can say it is also a kind of computational device. So that means Turing machine should also have an encoding. Okay. So how to encode Turing machines? How to encode Turing machines? So how can we encode Turing machines? So let's see. Encode means how we can represent Turing machines in binary. Okay. So let's discuss encoding of a Turing machine. Encoding of a Turing machine. Let's see. Okay. So to encode a Turing machine, we should store, or we can say we should have all the details of a Turing machine in binary format. Okay. So what are the details of a Turing machine? The details of a Turing machine are its transitions. Okay. What does that mean? So let's suppose we have a state Qi and we have a state Qj. Okay. Now, if we know that if I am in state Qi, okay, input is AI, let's say AI is input, then I will go to state Qj. I will rewrite, so rewrite, because Turing machine is doing 3 things. It is moving to a new state, rewriting something on the input tape, and then moving left or right. Okay, rewrite, let's suppose it is rewriting some string. Let's say string is SL. This is the string. It is rewriting this string on tape, and then movement. Let's suppose it is doing a movement. So how many possible movements are there? Are 2 possible movements, left or right. Let us represent left with 0 and right with 1. Okay. Now we have these transitions. How many such transitions are possible in a Turing machine? There are multiple transitions possible. There are n number of transitions. N number of transitions. So if we are able to represent these n number of transitions in binary format, that means we can represent the entire Turing machine in binary format. Okay, let's say there are 5 states of a Turing machine. How many states? 5 states. Okay. Let's say state is Q0, Q1, Q2, Q3, and Q4. How many states are there? 5 states. Now, can we represent these 5 states in binary? Yes, we can represent every state in binary. How many states are there? 5. So how many bits are required? 3 bits. So 0, 0, 0 will represent this one. 0, 0, 1 will represent Q1. 0, 1, 0 will represent Q2. 0, 1, 1 will represent Q3. 1, 0, 0 will represent Q4. Okay. So every state can be represented with binary. Let's suppose there are 2 inputs, A and B. So A can be represented with 0 and B can be represented with 1. Now we have string SL. So let's suppose this string can be anything. Okay. Even this string can be represented in binary because every string can be represented in binary. Then this left and right movement, this can also be represented in binary. So we have to store these 5 things. Okay. And how many these 5 things we have to store? N 5 things. Let's first store these things. These 5 things is also called a quintuple. Quintuple means 5 items. So in every transition, we have to store 5 items. So what are the 5 items? Qj, Aj, Qi, Sl, and movement. These are the 5 things that we have to store. Okay. So these 5 things means that, see, this Qj means the final state it will go to after consuming Aj means the input, Qi means the current state, Sl means the string that it is going to rewrite on the tape, movement means whether it will go into the left direction or right direction. So this can be represented in binary. This can also be represented in binary. This can also be represented in binary. This can also be represented in binary, and movement can also be represented in binary. So all these 5 things can be represented in binary. So every quintuple, can be represented in binary. Okay. Now this is quintuple 1. I will write in capital quintuple 1. Now how many such quintuples are there? N. So we have quintuple 2 dash 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 quintuple n. Quintuple n. Now quintuple 1, it is in binary. Okay. Now we will combine this binary with this one, quintuple 2, but we will separate these by 2 zeros. 2 zeros means that on this direction, this is a separate quintuple and this is a separate quintuple. Then we have again 2 zeros. You can use 2 zeros, 3 zeros, 4 zeros, whatever representation you want to use. Okay. So that means all quintuples. So we have quintuple 1 separated by a binary. Let's suppose 3 zeros. Then we have quintuple 2. Then 3 zeros, quintuple 3, 3 zeros, dash dash dash. At the end, we have quintuple n. So that means this complete binary string. So this is a binary string because everything is in binary, 0 and 1. So this binary string represents a Turing machine. Or we can say this binary string is the encoding of a Turing machine. Since it is an encoding of a Turing machine, so how many Turing machines are possible? There are millions and trillions of Turing machines possible. And every Turing machine can be represented by a binary string. So we can write that every Turing machine can be represented by a binary string. So, but this binary string should be well formatted. What is the meaning of well formatted? Well formatted means, for example, if I have a binary string this, so you will say, does this binary string represent a Turing machine? No. Why? Because only those binary strings will represent a Turing machine where we have quintuples and they are separated by 3 zeros. So there is some specific format. So there is some specific formatted binary strings that represent Turing machines. Formatted binary strings. So we can say that every Turing machine can be represented by a binary string. To simplify it, we can also say that every binary string represents a Turing machine. Every binary string represents a Turing machine. But here I said that this kind of Turing machine, this kind of binary string does not represent a Turing machine. But here I am saying that every binary string represents a Turing machine. So it is a contradiction. Okay. So here I am contradicting my statement. So to simplify it, what we will say that if we have an L formatted binary string like this one, we will say that L formatted binary string also represents a Turing machine, but language of that Turing machine is phi. Phi means that that particular Turing machine is useless, or we can say that Turing machine does not accept anything. Okay, and every well formatted binary string represents a Turing machine that has some language. So from this we have an important illustration or observation that every binary string represents a Turing machine. Okay. Every binary string represents a Turing machine. So you have to keep this in mind. But you have to also represent that every L formatted binary string means a Turing machine that accepts nothing. So that means epsilon, it is a Turing machine, 0 is a Turing machine, 0, 0 is also a Turing machine, 0, 1 is Turing machine, 1, 0, dash, 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 all binary strings represent a Turing machine. And from this, we can say that Turing machines can be enumerated, or we can say ordered in some order. We can place Turing machines in some order. For example, epsilon means Turing machine 0. 0 means Turing machine 1. Likewise, we can order Turing machines because of this encoding, this particular encoding. So what I am saying that Turing machines can be enumerated, okay, or they can be ordered. So I hope you understood the concept of encoding of a Turing machine, how we can encode a Turing machine. So now let's go back to our main point. So we were saying that we have a Turing machine. So this is the Turing machine. and it is taking an input, and we said that every input can be represented in binary format. So binary string takes an input and it can accept this or reject. Reject means no. Accept means yes. Yes answer and no answer. So that means we can encode any problem as a binary string and a Turing machine can answer a query on the problem. So what I am saying that any problem can be encoded as a binary string. Binary string. Okay. Any problem can be encoded as a binary string and a Turing machine can answer a query on that problem. Okay, fine. Now another question here arises is that, for example, we said that Turing machine represents a computer. Okay. It is same as a computer. Does we have a separate computer for separate problems? No. We have a single computer, and we can give multiple problems to this computer. Multiple problems. And then this computer solves this problem, provides the solution to every problem, whatever problems we give. Now, whatever we are understanding up to this point, we are saying that if we have problem one, or we can say language one, we have a Turing machine, one for that language. Okay, we have another language, we have another Turing machine, we have another problem, we have another Turing machine. So that means for every problem, we have a separate Turing machine. For every problem, we are having a separate Turing machine. But that is a cumbersome problem, or we can say, but that is not what is feasible in the real world scenario. We want a single device that should be able to solve multiple problems. So what I am saying here, that we want a single Turing machine that can solve all problems that can be solved by any Turing machine in the world. Okay, what I am saying that we have a single Turing machine. So this is our Turing machine. And now we were having multiple Turing machines, or we can say all possible Turing machines in the world. Let's say it was solving problem L1 and it was solving problem L1. So we want a Turing machine such that it can solve, or it can accept all recursively enumerable languages. Okay, what does that mean? We want a Turing machine such that the input to this Turing machine is a Turing machine, some Turing machine plus string. Okay, some Turing machine plus string, or I can say a Turing machine plus string encoding of this. because we know Turing machine can be represented with binary and string can also be represented with binary. So these together forms a binary string. So we want a Turing machine such that it takes these kind of inputs. So what is the input? The input is a Turing machine, some Turing machine plus string. And this Turing machine answers accept, or we can say it says accept, it answers yes, and it answers reject. Reject means it answers no. So it, and the another is it goes into a loop. So these are the three possibilities. This particular Turing machine, what is its input? Input is TM1 and string. Now let's see what will be this output. The output will be accept. When it will be accept, if TM1 accepts W. Okay. The answer will be reject if TM1 rejects W. And the answer will be loop. It will go into a loop if TM1 goes into this particular TM that simulates all other Turing machines in the world. This particular TM is called Universal Turing Machine, okay, which is also represented by UTM, Universal Turing Machine. So let's discuss this Universal Turing Machine in detail. So I will discuss this again, these things. So let's see what is a Universal Turing Machine and what is the language recognized by a Universal Turing Machine. So let's see what is a Universal Turing Machine. So let's see what is a Universal Turing Machine. Universal Turing Machine. Okay. So as I said that we are saying that our Turing machines, they are same as our computers. Okay. But you know that what is a computer? What is a general computer? For example, this is our computer. What is this computer doing? If we are having some problem, let's say any problem here, and we want to solve this problem. How we do this in real world? In real world, to solve a problem, we design a program for that problem. Okay. So program, we can say that we design a solution. Okay, fine. Then we give an input to this problem, to this program. This program runs on this input and it gives us the final solution. So for every problem, there is a program, okay, and that program takes the input and this program is the solution. It gives us the final output. We can say the final output. So how our computer works? Whenever we have to solve a problem, we give a program to this computer. Okay. And we also give an input. This computer runs this program, okay, on this input and it gives us the output. Fine. Likewise, if I have another problem, I will have another program. I will run that program on this computer, and this computer will take an input and it will run that program on that input, and it gives us the output. Okay. That is the general working of a computer. So we can say that a computer simulates other programs. So we can say computer is also a program, a kind of program. Okay, it is a kind of program, or we can say programmable device, but it is a universal program. Universal program means that this particular computer takes other programs and it runs those programs on the inputs and it gives us the output. Okay, so let me elaborate it. So what I mean to say here is that our computer, so this is our computer, we can say it is a universal program. Universal program. Okay. And what is this universal program doing? It is taking an input, a program, and takes an input, some input. It runs this universal program, runs this program on this input. So whatever is the behavior of this program on this input, that will be the output here. So how many programs it can run? It can run infinite programs. Okay. Likewise, in the Turing machine world, we have a Turing machine. So what is a Turing machine? It is kind of a computational device to solve a problem, to solve some problem. So that means our Turing machine is kind of a program, because program is also something that solves some problem. And like programmers take input, some input, and after taking the input, they will give us some output. Similarly, Turing machines also take input. Okay. So for every program or for every problem, we have a Turing machine. So instead of having millions of Turing machines, why can't we have a single Turing machine called Universal Turing Machine? And the job of this Universal Turing Machine is that whenever it has to solve a problem, we will give an input. Like here we have a program, input will be a Turing machine and some string W. Okay, output will be yes, yes means accept, or reject, or loop. Okay. So this Universal Turing Machine, what it is doing, it is running this Turing machine on this input. Like we have here in the computer world, computer runs a program on an input, and the output will be the same as the output of this program on this input. So the output of Universal Turing Machine is the output that we will get when we run this Turing machine on this string. So we can say Universal Turing Machine is a Turing machine that simulates all other Turing machines. Okay, so we have a Universal Turing Machine. universal Turing machine. Okay, and what it takes input the encoding of a Turing machine and a string, and the output will be accept if Turing machine M, so M is a Turing machine, accepts W is the input. Okay, and the output of universal Turing machine will be reject if this Turing machine M rejects W, and the output will be loop if M loops on W. So that means this implies universal Turing machine is a powerful machine, so that it can perform any computation. It can perform any computation that could be performed by any feasible computing device. That could be performed by any feasible computing device. Because why it is a powerful machine? It is because universal Turing machine can simulate any Turing machine in the world. Fine. So universal Turing machine is a Turing machine whose input, which takes input some Turing machine and some string, and the output will be these three possible outputs. And every Turing machine, we know that every Turing machine has a language. Okay, so what will be the language of universal Turing machine? Language of universal Turing machine will be the encoding, this kind of encoding, M comma W, such that M accepts W. So it is the pair of all possible inputs and Turing machines such that the Turing machine M accepts W. Or in other words, we can write it is equal to encoding of M comma W such that M is a Turing machine and M accepts this W. Okay, M is a Turing machine and M accepts W. So this particular language, this is the language of universal Turing machine. It is also denoted by ATM. So what is ATM? ATM is the language of universal Turing machine, or it is also denoted by L. So ATM is a language of universal Turing machine. And we know that any language that is a language of any Turing machine, that particular language is recursively enumerable. So that means ATM is a recursively enumerable language. Why it is recursively enumerable language? Because it is accepted by Universal Turing Machine, and any language that is accepted by any Turing machine, that will be a recursively enumerable language. Okay, so that was all about the Universal Turing Machine. Now we have to prove one important thing, that is we have to prove that ATM is not recursive. This we have to prove. Prove that ATM is not recursive. We already gave that we have to get two languages, L1 and L2. L1 is a language, so I don't properly remember what was it. L1 is a language, let's say L1 is a language that is recursive but not L1 is a language that is recursively enumerable but not recursive. And L2 is a language that is a language but not recursively enumerable. So that means we have to prove ATM is not recursive. So we have to prove that ATM is L1. L1 means that it is recursively enumerable but not recursive. Okay, that we have to prove. That was the aim of this particular lecture. So we will prove this thing, that ATM is not recursive. We know that it is recursively enumerable, but we have to prove that it is not recursive. Okay, this is the first thing that we have to prove. We have to prove another thing, this L2. We have to find a language that is language but is not recursively enumerable. That means it is not accepted by any Turing machine. So let's first find this language, this L2, then we will prove this particular statement. Okay, so we will first find L2, then we will prove this L1, or we can say we will prove ATM is L1, or we can say ATM is not recursive. Okay, so let's prove first this particular thing. Let's find a language that is not recursively enumerable. Okay, so what is our aim? Aim is find a language that is not recursively enumerable. Okay, let's see how we can find that. Let's consider one language, this language. LD is equal to, it is a language, X belongs to 0, 1 star such that, so this language, this particular language, it contains, what it contains? Binary strings. Okay, and we have also studied that every binary string represents a Turing machine. Okay, this thing we have already understood. So what it is saying, that LD is a language containing binary strings such that the Turing machine whose code is X does not accept X. Okay. So what does that mean? So we know that every binary string, what every binary string? So this is binary string, some binary string. So let's say binary string is X. We know that X represents a Turing machine. Why? Because every binary string represents a Turing machine. Now Turing machine takes an input, and we know by encoding all inputs can be written in binary format. So the input is also binary. So that means this Turing machine whose code is X, it is possible that input will also be X. X means some binary string. Okay. So if the code of Turing machine is X and input is also X, then only this X is part of this language if this Turing machine does not accept this X. So this is very complex. You have to understand it in great detail. So what I am saying, that what will be the strings in this language? So this language contains those strings such that the Turing machine whose code is X, it does not accept it. It is encoding. It is same encoding. Okay. Let's suppose we have a Turing machine. Its encoding is this. So let's say, for example, okay. So that means this represents a Turing machine. So this is our Turing machine. Let's name it TM1. Now this TM1, it takes input binary strings. So it is also possible that one of the binary string may be, or we can say one of the input may be this kind of input. Now this is the input, and Turing machine 1 has, it is encoding same as the input. So if it accepts this one, this input, it is encoding, then this string won't be a part of this LD. However, if it does not accept it, it is encoding, then it will belong to this particular language. Okay. So you have to first understand this language, then only you will understand the remaining part of this particular portion. Okay. So what I am saying, LD is a language, binary strings such that the Turing machine whose code is X does not accept X. Okay. And we will prove, so we will prove that LD is not recursively enumerable. Okay. So let's prove it. So let's prove it. Okay. So let's see the solution. So we have to prove LD is not recursively enumerable. Let's do one thing. Let's assume LD is recursively enumerable. So we are assuming that LD is recursively enumerable. So if LD is recursively enumerable, what does that mean? It implies there exists a Turing machine that accepts LD. Okay. So it means there exists a Turing machine that accepts LD. And we know that we have already discussed that every binary string represents a Turing machine. So that means epsilon 0, 0, 0, sorry, 0, 1, 1, 0, 1, 1, every binary. So let's suppose this is 0th Turing machine. This is first, this is second, this is third, fourth, fifth. So we have already discussed that Turing machines can be ordered. Okay, Turing machines can be ordered. Here I am saying that there exists a Turing machine that accepts LD. Let's say that Turing machine is, let's say that particular Turing machine is RE Turing machine. RE Turing machine. Fine. So we have a Turing machine that accepts this particular language, LD. Okay. Fine. So that is RE Turing machine. Let's say, so here, let's say the encoding encoding of that Turing machine is X. So this is the encoding of Turing machine. Fine. Now let's see. Let's now write case 1. Now what is X here? So it is a binary string. And this binary string represents a Turing machine that accepts LD. Now let's take this X as an input. Okay, some string, some input string. So then there are two possibilities. One possibility is X belongs to this language. Okay, because we know that X is a binary string. So one possibility is that X belongs to this language, and another possibility is X does not belong to this language. Okay, these are the two possible cases. One is that this binary string belongs to the language, this LD. Okay, and another case too is X does not belong to this particular language, LD. Let's take case 1. So what I am saying, that X belongs to LD. Okay, so when will be this binary string a part of this language? So it will be a part of this language when the TM whose code is X does not accept X. So from here, it implies when we are saying that X belongs to LD, that means the Turing machine that accepts X, the Turing machine that accepts X, the Turing machine whose, let me rub it. Okay. So it means the Turing machine whose code is X, does not accept X. Okay. So the Turing machine whose code is X, which is the Turing machine whose code is X? So this is the Turing machine whose code is X. What was that Turing machine? That was RF Turing machine. So this implies RF Turing machine does not accept X. Okay. Now, we said that X belongs to LD. So this X belongs to this language. Okay, this particular language. So what I am saying here, I am saying that X belongs to LD. What does that mean? It means that X belongs to LD. Now LD is a language. Okay, this is a language, and this language is accepted by RF Turing machine. Here we said that LD is recursively enumerable. That means there exists a Turing machine that accepts LD. And we said that Turing machine is RF Turing machine. So that means RF Turing machine accepts LD. So if this Turing machine accepts LD, that means it accepts every string that belongs to LD. And we are saying that X belongs to LD. So that means this implies RF Turing machine accepts X. Okay. So here I am writing. So I will write, we said that X belongs to LD and RF Turing machine accepts LD. So this implies RF Turing machine accepts X. Okay. So now let's see what is the issue here. So here I am saying that RF Turing machine accepts X, but here I am saying that RF Turing machine does not accept X. So here I am saying RF Turing machine does not accept X, but here I am saying RF Turing machine accepts X. So there is a contradiction. Okay. Contradiction in this case. Now let's come to case second. Now the case 2 is X does not belong to LD. What does that mean? This implies, so when we are saying that X does not belong to LD, so what is LD? LD means that those strings will belong to X such that the Turing machine whose code is X does not accept X. When we are saying X does not belong to LD, that means this implies Turing machine whose code is X accepts X. Accepts X. Okay. So what is that Turing machine whose code is X? That Turing machine is RF Turing machine. So this implies RF Turing machine accepts X. Okay. So this is the first thing. Now let's see what I am saying. X does not belong to LD. So LD, we said that X does not belong to LD, and RF Turing machine accepts LD. Okay. So that means this implies, so what does it imply? It says that RF Turing machine accepts LD, and whatever is not in LD, so since X is not in LD, that means RF Turing machine does not accept X. So that means RF Turing machine does not accept X. Okay. So here again we have two statements. One is RF Turing machine accepts X, and another is RF Turing machine does not accept X. So here also we have a contradiction. So in both these cases, in case 1 and case 2, we have a contradiction. So since there is contradiction in both the cases, this implies our assumption is wrong. What was our assumption? Our assumption was LD is recursively enumerable. So this implies LD is not recursively enumerable language. Okay. So we have proved that there is a language that is not recursively enumerable. And what was that language? LD language. So please understand that here we have made two cases. In one case, we are saying that RF Turing machine does not accept X. That is by the definition of LD. And we are also proving that RF Turing machine accepts X. That is because of this assumption that LD is recursively enumerable. Likewise, in case 2 also, we are saying RF Turing machine accepts X by the definition of this language, and we are proving RF Turing machine does not accept X by our assumption LD is recursively enumerable. And in both the cases, we reached a contradiction. So that means our assumption is wrong. What was our assumption? Our assumption was LD is recursively enumerable. So that means LD is not recursively enumerable. Okay. So we have proved, we have found a language that is not recursively enumerable. That means we have found a language L2. that is language, but it is not a recursively enumerable. Okay. Now we will prove that ATM language is not recursive.